Hello everyone, my name is Chiwan, or you can call me Aki. I'm honored to be here to share our recent research findings with you. The topic of today is Break the Wall from Bottom, automated discovery of protocol-level efficient vulnerabilities in web application firewalls. First, I want to briefly introduce the web application firewalls. It's now the most popular protection for web applications as it can block exploits with rules written by security experts. This has been a requirement for many industrial guidelines such as CIDSS and HIPAA, and the market share of WAF are continuously growing. As we all know, Log4j Shield is one of the most damaging vulnerabilities in the history of the Internet, and the research by Cloudflare WAF team shows that attackers have been looking for ways to bypass the WAF. After the initial payloads get blocked, the attacker applied encoding methods and Log4j support features to try to bypass the WAF. So how does the WAF detect malicious requests? The working principles of WAF can be divided into three strategies. First, it will paste HTTP messages to extract the HTTP parameters. Then it will match the parameters with the rows, and if any rows match the parameters, it will take the action written in the rows. For example, in the figure, an attacker tried to send a circle injection payload in the JSON body, and the WAF will paste the JSON body, and then extract the parameters. Since it's matching the circle injection rows below, the WAF will reject the request, which means the request won't be forwarded to the server. So a common way to bypass the WAF is to craft a payload not in the rows of a WAF. For example, the attacker mutates the circle injection payload with case conversation, and because in this example the rows of a WAF is weak, so the attacker can easily bypass the WAF. However, in the real world, the WAF has much more mature and strict rules, like there are over 5,000 rows in the CIS, so it's hard to bypass commercial WAF. There are works such as WAF-AMOR using adversarial machine learning to craft circle payloads that can bypass WAF. But as the circle and the JavaScript have different grammar, the bypass circle injection samples cannot be used to launch a cross-site script attack. Now let's rethink the three strategy of WAF detection. The correct detection process actually relies on the correct pacing result for HTTP parameters. To bypass the WAF, we can modify HTTP requests rather than the malicious payloads. As in the demo, an attacker changed the content type into XWordF-JSON, then it can magically bypass WAF. The reason is that the WAF cannot recognize XWordF-JSON while the WebAPI can. So even though the WAF has much more mature and adequate circle injection detection rules, it failed to block such a simple circle injection payload. Despite the concept of protocol-level evasion had been proposed in Black Hat USA for years, we found that the majority of protocol-level WAF evasion has been discovered manually, which may result in some evasion cases being overlooked. As we know, fuzzing is proven efficient in mining memory bugs. So how about using fuzzing to systematically and efficiently mine for all protocol-level evasion cases? The first challenge is to generate and mutate testing requests efficiently. It needs to meet two requirements. First, for correctness, the test inputs must keep contain the original malicious payload. Second, the search space should be close to legitimate HTTP messages to reduce testing invalid HTTP messages. To achieve these goals, we use AST-based and payload-aware test inputs rather than the raw messages, so that we can frozen the payload node to keep correctness and limited search space based on the grammatical guidance. The second challenge is to test the black box WAF efficiently. As many commercial WAF are closed source without code or binary, most fuzzing approach are black boxed. However, they can only generate test inputs binary, which is inefficient. Considering that there are many open source HTTP pacers in web developer frameworks, we can utilize this code coverage of these pacers to guide the fuzzing process for WAF as both pacers are implemented to pace HTTP requests. The third challenge is to detect WAF evasion cases automatically, unlike the legacy fuzzing process, which automatically detects bugs by programming exceptions such as crash or hangs. However, perk level WAF efficient are silent and won't trigger any crashes. So we need to design a new detect mechanism to detect and verify the efficient cases. We built the WAF validators to indicate whether the request can bypass through, and the WebApp validators to extract the parameters that this WebApp are actually using. The detector will collect the successful efficient samples when the WAF validators and the WebApp validators are both passed. So here is our fuzzing framework to automatically mine product-level WAF efficiency, and we name it WAF Menace. The left part is white box testing. In this part, we build an AFLI prototype to fuzz HTTP requests with open source WebApp. First, we collect HTTP grammar and use them to generate initial samples. These samples are constructed as an AST and they will line up in the crops waiting to be mutated, dumping to raw messages and then sent to the WebApp validators. WebApp executors will collect the code coverage and rearrange the queue in the cross to prioritize testing promising requests. In the black box testing strategy, we will send the valid HTTP requests that can paste by WebApp validators to the WAFs and collect the forwarded requests to re-verify the requests that still can be paced by WebApp validators. We also create an efficient sample centrifug to minimize the requests and the feedback to the crops. All the verified samples will be stored in efficient samples. We will talk about these details of these components in the following slides. The generator, its job is to help the framework generate initial inputs with HTTP grammar guidance. We first extract ABNF grammars from AVS standards, and the generator will start to build an AST from start symbol. In these samples, we start with the body symbol, and the generator will derive the symbol with grammar into dash boundary symbols, body part symbols, and closing boundary symbol nodes. These symbols will further derive until it reaches the terminal nodes, which is raw strings. Then we can get a fully expanded AST as our test input. When sending to the server on the test, we will dump this AST into raw messages like the one in the right upper corner. To be clear, we stored our input as AST rather than the raw messages in the testing process, so that we can mutate the test inputs in both grammar level or byte level. For grammar level, we can duplicate, delete, and remove non-lib node in the AST. For byte level, we can delete or add bytes in the lib nodes and encode the lib nodes. The figure below shows the mutating process. The mutator duplicates the body part subtree and deletes bytes in dash boundary node, so the corresponding messages will turn to the examples shown on the right. Specifically, we not add or delete bytes to the payload node to ensure the samples can be further applied to any payload. Validators play important roles in the WAF menace. They help the framework to recognize how WAF and WebApp process our tested requests. As the example codes below, we develop WebApp validators to echo the parameters it's actually using. For WAF validators, it will always return with the special stage code and the exact HTTP request in its response. Although there are many ways that WAF return a block page, we can quickly know the request apart as soon as we see the special stage code, and we can get the exact forwarding request to avoid false positives caused by normalization of the WAFs. In the black box testing strategy, centrifug can help WAF menace to minimize and re-verify the vision by iteratively removing useless nodes on the AST. First, it will randomly delete node in the AST and send to WAF validators. If the sample still bypassed WAF, we will send the real request in the response of WAF validators to WebApp validators. If samples still paced correctly by WebApp validators, we can see that the node is redundant, so that The scientific can also help us to find unique samples like the sample C and sample D, and the two-step validations can help us to exclude false positive samples.
In the evaluation, we select top 20 popular open-source web app frameworks and 40 mainstream web. For the setup of taint payload, we use an unobfuscated attacker payload that will be detected by the WAF without mutating the HTTP request first.
After evaluation, we found two interesting facts. The first is that all tested web framework actually accept some non-regular requests, and the second is that most of WAP can be bypassed with specific HTTP requests. After manually analyze its efficient cases, we summarize three protocol-level WAF efficient tactics. The first is malformed parameter structures, and the second is parameter type confusion, and the last is RPC spot gap. We found 3,011 efficient samples across 40 by 20 WAF and WebAP combination. We have seen that some WAF are very strict like NASIS or mod security, and some WAF do not paste the body. But we still find approaches to bypass this WAF. So let's talk about the three tactics. First of all, the parameter type should be identified correctly to help WAF extract the same parameters as the WebAP. We found that we can make a fake content type headers to mislead the WAF to choose wrong type to paste the body parameters. In these examples, the mode security synced body is XML, while the Flash app will use the last content type to indicate the body type. So magically, attacker can leverage these tactics to launch circuit injection attack even with strict circuit injection rules. In this case, we found that an attacker can make Alibaba Cloud WAP believe that he is transforming a file parameters rather than a normal parameters. After add two CRs, content transfer encoding and file name, the WAP pages will synchronize a file because there's only one headers and there's a file name parameters, while PHP will paste this as normal parameters because he synced the CR as line separators, so there are two headers in the part, and there's no file name parameters in the content disposition headers. For tactic 2, attacker can construct malformed data that the WAF cannot paste while the WebAP can. The difference between tactic 2 and tactic 1 is that while the WAF chooses the correct pacer, it cannot extract the correct parameters while the WebAP can. In these examples, we find that the attacker can craft the boundary parameters with a quarter, and the Cloudflare WAF will not paste it correctly, while most of WebAP correctly paste the body. In the next case of these tactics, we found the interesting fact that PHP-based apps are very tolerant of malformed HTTP messages. You can see that after the attacker had deleted the closing boundary and the form data tokens in the content disposition, the PHP-based app can still extract the correct parameters while the Fortinet WAF do not, so that the attackers can use these tactics to bypass Fortinet WAF and launch circuit injection or command injection attacks to the PHP-based web app. For tactic 3, we found that there are many deprecated or extended features in the related RPC standards. An attacker can use features spotted in WebAP but not in the WAF to evade the detection. The difference between the tactic 2 is that the attacker actually crafts a formal request that should not trigger WAF spacing exceptions. In these examples, we found the attacker can encoding his malicious payload with code printable, while we find that in RFC 7878, the recommendation of content transfer encoding got deprecated, and the sender should not generate any part with content transfer encoding header field. However, the goal-based app still supported, so that the attacker can use these tactics to bypass WAF and launch circuit injection, command injection, on the goal-based app. In the next case of these tactics, we found that Django app supports char set parameters even the content type is UI encode, and most WAF will not paste the char set parameters in this MIME type, so that the attackers can use UTF-7 to encode his malicious payload and bypass WAF like Microsoft Azure to launch circle injection or comma injection attack to the Django app because he will decode the HD body with the char set parameters. After we discover these efficient cases, we soon report them to related vendors. Specifically, when the root cause is that WebApp didn't follow the standards, we choose to report to the WebApp framework. Until now, 11 vendors have received the reports and 9 vendors have conformed, with 8 vendors fixed. To sum up, our work underscored the unfortunate fact that the pacing process had become an Achilles heel in the WAF defense. We design and implement a new protocol-level WAF efficient fuzzing frameworks called WAF Minis, which can mine protocol-level WAF efficient vulnerabilities with code coverage guidance. We summarize 3 tactics in payload-level efficiency and found 3011 efficient cases on 40 by 20 web app and WAF combination. So that is all my presentation. Thank you for your listening.